Okay. So last time we dealt with some part of measurement, and we were dealing with the measurement of resistance. I don't know if you can hear me. Confirm. So I'm saying we dealt with the measurement of resistance. Today we are going to deal with the measurement of power. This is still under topic 2, which is a little bit longer, but the others are short. So once we are done with this topic, and this is the basic of the whole Emfd unit. So once we are done with the measurement, the other topics will be easier to deal with. So there is no need for worry. So I'm saying that we are going to proceed with the measurement of, and kindly ensure that you are muted. Ensure you're muted. So we all know what is power, and we in engineering we have power in two major forms: power as a result of DC, and power that results from the alternating current. We are going to look at all of them, and maybe we can go through this introduction here, that measurement of electric power is as essential in industry as in commercial or even domestic application. And prior estimation and subsequent measurement of instantaneous and peak power demands of any installation are mandatory for design, operation, and maintenance of the electric power supply network feeding it. And whereas an underestimation of power demand may lead to blowing out of power supply side accessories, on the other hand, overestimation may lead to over-design and also additional cost of installation and also maintenance. Knowledge about accurate estimation, calculation, and measurement of electric power it will be our primary concern, and because you are the designers of the new installation that is in the near future. So in this chapter, most popular power measurement methods and instruments will be discussed. So this is a subunit. We are going to start off with the measurement of power in DC circuits. Measurement of power in DC circuits. We all know what is DC circuit, and this is the easiest when you talk of measurement of power, because you're just going to use the simple calculations that arises from like you can see that power is equals to I squared R, or V times I. That is the voltage of the load, and the load is what you are going to signify as R. That is the source of the resistance in the circuit, times the current that is flowing in the circuit. So electric power consumed by the load R, this is our load going by the figure 7.1, will be calculated by multiplying the voltage across the load times the current that is flowing in the load. You can see that this current here, the resistance here, or the load, it is connected in series with the supply voltage, that is the VS as per the illustrations. So that is the product of the voltage across the load, that is the VR, and the current that is flowing through the load, that is IR. And therefore, measurement in DC circuits can be carried out using a voltmeter and the ammeter. And we know last time I was trying to explain that when you're using a voltmeter, the analog voltmeter, whatever you're trying to measure the voltage across it, you arrange your voltmeter in such a way that it is in parallel with the load, And the ammeter for this case, as you can see from the illustration, the ammeter is in series with the load, with the R and the source. So these are the two arrangements for power measurement in DC circuits. One thing that should be kept in mind while using any of these two measuring arrangements, as shown in the figures here, is that both the voltmeter and the ammeter, they will require their own power, their own source of power. So you will need to power the voltmeter and the ammeter separately. And the explanation is that in figure A, this figure A here, the voltmeter is connected between the load and the ammeter, you can see. So the voltmeter is connected between the load, the R, and the ammeter, you can see here. And the ammeter, therefore, in this case, measures the current that is flowing into the voltmeter. Current that is flowing into the voltmeter. Therefore, the IV, that is the current that is flowing in the voltmeter, we know how to calculate IV, or the current in a circuit, because from the Ohm's law, I is equals to the V over R. From the Ohm's law, V equals IR. Therefore, I is equals to V over R. And therefore, the current that will be flowing here through the voltmeter will be equals to the voltage, that is the VR, divided by the resistance of the voltmeter. So the current through the voltmeter of the IV will be equals to VR, that is the voltage through the resistor or the load here, divided by the resistance of the voltmeter. Very important to understand for those who have been a little bit serious reading the notes that I usually share. We said that this is when we are tackling the measurement of DC and AC voltages and currents. We say the voltmeters, the ammeters, they themselves, they possess their own resistance. And that's why we're saying that for you to get the current that will be flowing through the voltmeter, remember this is its own current, the current through the voltmeter, you take the voltage through the resistor or the load, and that can also be assumed the voltage through the voltmeter, because they are in parallel, so therefore we know voltage in parallel connections is the same. So the voltage, and it will also be the voltage through the source. So it will be the VR divided by the RV, the RV being now the resistance of the voltmeter, and that is the internal resistance. And so for you to calculate the power that is consumed by the load by using the arrangements of figure 7.1a, we have said power is equals to V times I. So you'll take power that is consumed by the load, that is V, it will be now VR, that is the voltage of the resistance. The R for this case, you're assuming it is the load, times the IR being the current through the load, the resistance. And we have seen from the explanation, this can be expanded further. Let us look at this explanation here, that power that is consumed by the load is equals to VR times IR, and this can be expanded further because we know IR will be the IS, that is the resistance, the current, or the total current of the circuit, minus the current that is flowing through the voltmeter. This takes us back to the issue of the Kirchhoff's current laws, and we know that the algebraic sum of the currents that enter a junction is it is 0. So looking at this junction in figure 7.1a, looking at this junction here, we can see that we have 3 currents here. So there is the IS, IR, and IV. IS being the current from the source, current from the voltage source, and that is the total current that is being measured by our ammeter for this case in A. And there is the IV, which you have said is the current through the voltmeter. And also there is the IR, which is the current through the resistor. The resistance being the load for this case. So that's why we're saying, according to the Kirchhoff's current laws, we have said IR will be IS minus IV. And also IS is equals to IR plus IV. And also IV is equals to IS minus IR, such that the algebraic sum of the two of those three will be equals to 0. So therefore, VR will be equals to, now opening up the brackets in this, you can see this explanation here. So we have solved up to this point where I've explained where we get IS minus IV. So we can open up these brackets and say that VR will be VR times IS, that is the supply current, minus VR times IV. And we can expand all these to get us to equation 7.3 that says that the power indicated, the power that is consumed by the load, power consumed by the load, we can call it the PR, power by the load for this case being R, is equals to the power indicated by instrument, power that is indicated by instrument, minus the power loss in the voltmeter. Remember, our instrument here being the voltmeter and the ammeter, these are mechanical instruments, these are not digital instruments. Therefore, the mechanical instrument, the nature of this type of instrument, there will be power losses. And that is the explanation according to figure 7.1a. Going on to figure 7.1b, and see how the connection is. Maybe you can go back and look at how the connection is. You can see now the ammeter is measuring the current. You can see the position of the voltmeter. The voltmeter is between the source, that is the VS, and the ammeter, and also the load. So in that figure, the arrangement B, the voltmeter measures the voltage drop across the ammeter, and in addition to that, dropping across the load. And we can now represent that information mathematically, such that the PD drop, that is the voltage drop across the ammeter, will be equals, we can call it the VA, that is the voltage across the ammeter, which will be equals to IR, that is the current through the load, times the RA. We know V equals to IR. So the voltage drop across the ammeter will be equals to IR, that is the resistance, the current through the load or the resistance. I keep on repeating that the R for this case means the load, times the RA, that is the internal resistance of the ammeter. We're saying these instruments are mechanical, therefore they experience some losses. So with that in mind, the power that is consumed by the load will be equals now to the power that is indicated in the instruments minus the power loss in the ammeter. That is the opposite of what we did in figure 7.1a, where we said that the power consumed by the load is equal to the power that is indicated by the instruments minus the power that is lost in the voltmeter. And this is due to the arrangements of how you arrange your instruments, your measuring instruments, or the position, or what matters here is the position of the voltmeter. So for figure 7.1b, the total power consumed by the load, or the power that we want to measure at the load, will be equals to the power that is indicated by the instrument minus the loss or the power loss in the ammeter. And there is that the explanation that is explained here by the equation 7.14 and 7.15. So with all that in mind, the power that is indicated equals to the power that is consumed plus the power loss in the ammeter. Power that is indicated equals to the power that is consumed plus the power loss in the ammeter. And therefore, both arrangements indicate the additional power absorbed by the instruments, in addition to indicating the true power that is consumed by the load only. The corresponding measurement errors are generally referred to as the insertion errors. I don't know if there is any question before we look at this example 7.1. Any question from the class? So we are going to look at this example 7.1. Example 7.1. You can copy that example in your notebook. Then we look at the working, how what you are supposed to do with this. Actually, you can try it. Then we are going to look at it together. So attempt example 7.1. I hope you have drawn the two arrangements. So attempt this example 7.1. Then we look at it together. And try to be quick. You know, for Zoom, it usually resets itself after every 40 minutes. So try to fasten a little bit. So I don't know if you have managed, but we can look at the working. So let us go through the question that reads, two incandescent lamps with resistances 80 and 120 ohms are connected in series and has a source of 200 volts, that is DC. We're told to find the errors in the measurement of power in the 80 ohm lamp using the voltmeter with an internal resistance of 100 kilo ohm and an ammeter that has an internal resistance of 0.1 mega ohm when A, so these are, we have different arrangements. A, when the voltmeter is connected nearer to the lamp than the ammeter, and B, when the ammeter is connected nearer to the lamp than the voltmeter. So we have the both. Let us look at the solution. We're going to go through the, it's already worked out here. We're going to go through the solution step by step. I hope that as we go through it, you're going to be taking notes and also be copying the correct working. So let us look at this solution here. So we have two arrangements. A, when the voltmeter, so we have two lamps, that is both, they are 80 and 120 ohms resistances. And we are told that they have different, we have the voltmeter that has an internal resistance of 100 kilo ohm and an ammeter that has an internal resistance of 0.1 mega ohm. And we have the arrangements, that is A, the voltmeter is connected nearer to the lamp than the ammeter. And for the case in B, that the ammeter is connected nearer to the lamp than the voltmeter. So these are the arrangements you can see for this case. So solution one, assuming both the instrument to be ideal, that is ideal, this means that they have in their impedances are infinite, and also the ammeter has zero internal impedance. The voltmeter, its impedance is infinite, and the ammeter, its impedance is zero or none. Therefore, it's assumed that the current through that the current that will flow, because they assume that they are connected in series, will be, so we all know how to calculate current. Current is equals to as per the Ohm's law, equals to V over R. V over R, because V is equals to I times R. So for this case, the V is the source voltage, and the source voltage as per the instructions are it is a 200 volts DC source, and you can see it here from the diagram. So the total current that is flowing here in this series connection will be 200 volts divided by, now the connection, assuming, we have said that we assume the impedances of the ammeter and the voltmeter. So they are connected in series, and we know the voltmeter, not the voltmeter, but the first, the one of the incandescent lamps is 80, and the other one is 120. So the total resistance, remember they are connected in series, will be 200, 80 plus 120. So for you to get the current that is flowing in this connection, and we are assuming with this assumption that the instruments are ideal, it will be 200 over 200. 200 over the 80 plus 120, that is the resistances of these two lamps. And the current will be 1 amperes. So that is the first assumption that you need to deduce. That is the current that will be flowing in this circuit with the assumption that these instruments are ideal. So true power consumed by the 80 ohm lamp would have been what? And remember, still going by the assumption that these instruments are ideal. what will be the true power that is consumed by the 80 ohm amperes. We saw how you calculate power. Power is equals to V times I. And you can expound that to say, we know V is equals to IR, that is current times resistance. So P power will be equals to I squared times R, that is the current square times R. We have seen the current to be 1 ampere, and we are assuming that they are connected in series. So to be 1 squared times R, the resistance going with the first one, that is the 80 ohm lamp resistance. So this will be 1 squared times 80, which will be 80. Then you can assume the other one also, I squared R, that will be 1 squared times 120. But however, considering the internal resistances of the, now that was working with the, assuming that these instruments are ideal, they don't have any resistance. So now that was the calculation as per the assumption. Now let us go to the actual calculations, factoring in the resistances that have been given in the question. That is the resistance of the internal resistance of the voltmeter, which is 100 kilo ohm, and the internal resistance of the ammeter, which is 0.1 mega ohm. So when we factor them in, we have this kind of arrangement. This is the kind of arrangement that you are talking about. So first of all, you can see there is the, now we are going to have some, we are going to have those resistances put in the circuit. You can see the 0.1 mega ohm, that is resistance for the ammeter, and also the 100 kilo ohm, that is the resistance for the voltmeter. And going by the first explanation, that is scenario A, whereby we are told the voltmeter is connected nearer to the lamp than the ammeter. So here it is. So we're going to have some assumptions. We're going to have the IS, that will be now, we're going to label that the supply current, Then we're going to have the IR, that will be the current through the resistance, the IV, the current through the voltmeter, and so on. So let us try and see what will be the supply, what will be the reading in the ammeter once we factor in these the errors that are resulting as factoring in the resistances of the instruments, that is both the ammeter and the voltmeter. So the supply current, or now the reading in the ammeter, will be what? We are going to just use the normal calculations to get the value of I, which we said it is 200. That is the V of the resistances. But for this case, we're going to factor in the resistances of both, because for the first case, we found that the I that we got at as 1 amperes, we just factored in the resistances of the lamps. That was 120 and 80. But for this case, we're going to factor in the resistance of the ammeter and also the resistance of the voltmeter, and we're going to see how they are arranged, because you can see, like for this case here, you can see the arrangement one here, the lamp one, this lamp that has 120 ohm resistance, it is in series with the resistance of the ammeter, assuming this is the ammeter, not assuming, but this should be the place of the ammeter, because that is indicated by the 0.1 mega ohm, that is the resistance of the ammeter as per the question. And also now the 120 ohm lamp is in series with the 0.1 mega ohm ammeter. So those two are in series. We know that the resistances in series, you just add. And also the voltmeter and this and the 80 ohm lamp, they are in parallel. You can see the connection here. So how do you deal with, how do you calculate voltages in parallel? That is the product of a sum. So that is what we are going to do to factor in the values of the total resistance in this circuit. So going straight to the and the supply voltage won't change because that one is not affected, because you have not been told that the supply has an internal resistance. So we are going to take, so for us to get the supply current or the reading in the ammeter, we are factoring in the resistances of the instrument. We are going to say 200, that is the supply voltage, divided by the total resistance. The total resistance will be what? You factor in these two, then you add the corresponding resistances of these two. So this one will be 120 plus 0.1 mega ohm. And then also, because that is they are in series, just add them directly. And then for this other case, it will be 80 ohm, that is in series with the 100 kilo ohm resistance of the voltmeter. So for you to get that the effective resistance there between the voltmeter and the 80 ohm lamp, you take product of a sum. So the product will be 100 kilo ohm, that is 100,000 times 80 divided by the 100,000 plus 80. And once you do all that, actually it is here. So the supply voltage divided by the series of lamp 1 and the ammeter plus the parallel of lamp 2 and the voltmeter. And that will be 200 divided by the 120 plus 0.1 mega ohm. This is, sorry, this is milli, not mega. This is small m. This is milli ohm. So times 10 raised to negative 3. And also now the 100 kilo ohm. So that is 100,000 times 80 all over the 100,000 plus 80. That is product of a sum. So once you do all that calculation, the supply current, that is the IS, or the current, the reading in the ammeter. Sorry, the reading in the ammeter is 1 point. You can see it's very, very, the error here is, or the difference between what we got when we assume that the instruments are ideal and this one, it is very minimal. So this, the supply current, the IS, is equals to 1.0003 amperes. You can confirm that using your calculator in a minute. So I hope everyone has confirmed that that value is correct. Actually, from my calculation is 1.000319 and so on. So rounding it off, it is 1.00032. So with that in mind, we can actually now calculate the current through the 80 ohm lamp. The current through the 80 ohm lamp. So this one, we are just going to use the current divider rule. We are going to say that we are going to see how it divides, because it's as the current is going to divide as per the current, the Kirchhoff's current law. That is the KCL, Kirchhoff's current law. So the total current is 1.0003, and then now times the value, that is the resistance in this side. So for us to get the value of the current through the 80 ohm lamp. So that will be 100 times 10, that is 100 times 10 raised to 3, then divide by 100 times 10 raised to 3 plus 80. and that gives us 0.9995 amperes. That is now the current through here. Once we have the current through the 80 ohm lamp, we can also get the current through the, once we have the current, we can also get the value of the voltage through the 80 ohm lamp. And that will be very simple because we know voltage is equals to the product of the current times the resistance. We have seen the value of that current is 0.9995, and then times the value of the resistance there, which is 80. So that will be 80 times the value of that resistance, 0.9995, and you get it to be 79.96 volts. So from that, the remainder of the 200, that will be the value of the voltage through the 120 ohm lamp. But we are not interested with the voltage as per se. What we are interested in is the power that is consumed by the lamp, the actual power that is consumed. And we know you get power is given by V times R. So the power that is consumed by the 80 ohm lamp will be the voltage through the 80 ohm lamp, which you have seen is 79.96 times the current through that times the current through that 80 ohm lamp. So 79.96 times now the value of the current, which we had seen is 0.9995, and that is the power will be 79.922 watts. 79.922 watts. So that is the actual power that is consumed by the 80 ohm lamp. I don't know if you are still together. Ensure that you follow keenly. So we have now we have seen the actual power that is consumed by the 80 ohm lamp. I don't know what the question was asking. You can go back and look at the question. The voltmeter, we're told to find the errors in the measurement using, okay. So that was for the scenario A, 79.922 watts. Now, what is the power consumption as indicated by the 2 meters? Power consumption as indicated by the meters. So we are going to see what the value that is indicated by the voltmeter times the value that is indicated by the voltmeter times the value that is indicated by the ammeter. So the ammeter, we saw it is indicating 1.0003 because we calculated that here. That is here when we factored in the resistances of the instruments. That was the resistance of the ammeter, which was 0.1 milliampere, and also the resistance of the voltmeter, which was 100 kilo ohm. So that is how we got the ammeter reading, or the total current in that circuit. And now we have seen the voltmeter reading. That is, we have seen the voltmeter reading. That is by calculating the value, the value of the voltage, that is the PD drop across the 80 ohm lamp. So with that in mind, you can just calculate. Now see, we have seen the actual power that is consumed. That is gotten by doing the calculation directly. That is the VR times the IR, which we have seen is 79.922. Remember, these values will be very, very, very close. So it is important for you to be able to use I advise students to use up to 4 decimal places for you to have accurate figures. You can see both of them, the actual power that is consumed and also the power, the apparent power that is indicated by that is calculated by taking the readings of both the voltmeter and the ammeter. So with that in mind, so we can get the power consumption as indicated by the 2 meters. So taking the voltmeter reading, 79.962, times 1.003, and you get 79.986. Note the difference between 79.922, that is the actual power that is consumed, and also the apparent power that is indicated by the 2 meters, that is 79.986. So we can go to the second scenario, whereby now the diameter is closer to the resistance as compared to the voltmeter. So we move the position of the ammeter. Note the difference between the two figures. You can see here the position of the ammeter here, and this is for the figure A, and also the position of the ammeter as per the figure 7.1b here. So this is the actual connection for the example, this example that you are tackling, 7.1b. So just going by the same analogy, we're going to try and get the supply current. So we are going to find the resistances. We're going to find the total resistances. We can see here how the total resistance will be. There is the first, the 120 ohm, 120 ohm lamp, and there is the 80 ohm lamp. So what would be the total resistance in this circuit? So you can see the 120 ohm lamp, it is in series with all the other connections here. How do you tell if a connection is in series or it is in parallel? I can try and help you, though this is semester 1, year 1, 1.1 work from the basic circuit analysis, but we'll try and see. So for you to know if the connection is in parallel or is in series, we just try. So from the source, we're going to try and see the flow of current. If current is dividing, then that one means that they are in parallel. If the current is flowing is in a uniform direction, then there is that connection is in series, because we know current in series connection is the same, but the current in parallel connection is not the same. So from the supply here, 200 volts, so there is that supply current that is through the 120 ohm resistance. You can see after that it comes and divides here. That is to be now the current. The IS will be equals to IR plus IV. You can see the current through the 120 ohm lamp divides into two, the IV and the IR. So whatever you're going to get for IS will be equals to IV plus IR. IV being the value of the current through the voltmeter, IR being the value of the current through the load, and also the 80 ohm load, and also through the ammeter, that is 0.1 milliohms. So for us to get the value, the total value of the resistance in this circuit, we are going to have the IV. For us to get the total value of the resistance in this circuit, in this when it is arranged in this manner, so you are going to take the 120 ohm plus. Now we get the total value of the resistances here, and we can see now the 0.1 milli ohm and also 80 ohm, they are arranged in series, and they are also in. So these two, that is the ammeter and the 80 ohm lamp, they are in series, but the two of them, they are in parallel with the 100 kilo ohm resistance, that is the voltmeter. So we are going to find the effective resistance. We're going to find the effective resistance, and whatever you get as the effective resistance across this loop, you add it to 120, and that is calculated here. 120 plus all of this. So here they are using product of a sum. Product being the voltmeter is in parallel with the 80 and the 0.1 milliohm ammeter. So once we do that, you take now whatever you get there, you divide it from the supply voltage, because we know value of I is equals to V over R. So 200 all over the total resistance in this circuit. and you'll get the value of the supply current, that is the IS, to be 1.003 amperes. So with that in mind, we can get now the value of the current through the 80 ohm lamp. Remember our interest, we are trying to get the power. So once we get the current, we can also get the voltage and also get the power. So what is the current through the 80 ohm lamp? We have seen the total supply current is 1.003. So using the current divider rule, we are going to find the total current through the 80 ohm lamp, and it will also be the current through the ammeter because they are in series, and as we have said, current in series is the same. So taking the current divider rule, we are going to find the current through the 80 ohm lamp, or the IR, to be 0.9995 amperes. And that, with that in mind, we can get the value of the voltage, or we can go straight away and work out the value of the power. We know power is equals to V times R, V times I, or I squared R. So we have the I, we have the R, we can get the power very quickly. So the voltage across, the PD drop across the 80 ohm lamp will be the current that is passing through that lamp times the value of that resistance. So IR times 80. IR is 0.9995 amperes times 80, and you get 79.96. What is the reading in the voltmeter? So the reading in the voltmeter will be what? You just need to get the V, the PD drop across the voltmeter, and that one you can get it by saying we know a V equals to IR, and we just need to get the PD drop. We need to get the value of the IV, because we've seen from this diagram here, we have seen that IS comes and divides. We have seen what is the value of IR. So what will be the value of IV? So IV will be IS minus IR. So IS, which was 1.0003, minus IR, which is 0.9995 amperes. Once you subtract the two, then times the value of the resistance here, you'll get the PD drop across this voltmeter, and that will be the voltage that is indicated in that voltmeter. So IS minus IR times 100 kilo ohm, and that will be 80 volts. That is the reading in the voltmeter. So what is the actual power that is consumed by the lamp? So the actual power will be the VR times the IR. The VR is 79.96 from the calculations here, and the IR is 0.9995 amperes. And once you multiply the two, you get 79.2. And now that is the actual power. What is the power that is consumed? So for you to get the power that is consumed, you take the reading that is in the voltmeter times the ammeter reading. The ammeter reading, it is the current, the IR. You can see, because we said the IR, that is the current through the 80 ohm resistance, is also the current through the 0.1 ohm, 0.1 milli ohm ammeter. They are in series, you can see here. So the reading will be what? The value, the reading in the ammeter will be the value of IR. So that is the value of IR. And for you to get the power consumption as calculated from by the two instruments, you take the value, the reading in the voltmeter, which you have seen is 80, times the reading in the ammeter, which is 0.9995. So once you multiply the two, you get 79.96 watts. So that is the apparent power, and we also have the actual power. So from there, we can go straight and calculate our errors. So this is so you just create. You can see the table that is created here. You create a table, or you don't necessarily have to create a table, but you just need to see the actual power and also the apparent power. and from there you can calculate the percentage error. So finalize on that, then we can maybe give you an example, and then we can conclude the live class. Also, you can raise your questions. Let me have the questions. If anybody needs any clarification, let me have them now. And that reminds me that the last question I gave you, most of you did not get it. And that is very worrying because it was a straightforward question. You had all the values, you just needed to put them in the calculator. So ensure whatever those are the value, you might not get time to work out the cat2. So that is what will be used to calculate your cat2 and assignment 2. So whenever I give you those assignments, ensure that you do them and you do them accurately. So copy that, and then let me have the questions. So for homework, not for homework because you have around an hour and a half or so. I want you to repeat the same example 7.1, but now change the values of the lamps. So you're going to repeat that same example, but now the value of the lamp, you change it to 50. I hope you're noting down, and ensure that you send this before 5 p.m. So repeat the same example, but now the values of the lamp, you change them from 80. Now you change it to 50, and 120 you change it to 120 you change it to 70. So that the question will read two incandescent lamps with 50 and 70 resistances. So I repeat, change the values of the lamps to 50 and the other one to 70, and attempt the question the way it is. So you're just going to change the values of the lamps, 50, 70, then the others remain the way they are, and you're going to work it out just the way that like we have done. You first calculate the current through the circuit, assuming that the instruments are ideal, and also now you proceed and work out the other values. For case A, that is when the voltmeter is nearer to the lamp, and for case B, when the ammeter is the one that is nearer to the lamp. I've not seen any question. I don't know if that means that we are all together or we are not together. That I will understand that when I see your work. So attempt that work, and let me have your working before 5. Also, before I forget, because we are operating outside the ZDS platform, ensure that you log into the ZDS platform so that the system can mark you present. So before the expiry of the time, that is before 5 p.m., ensure that you have logged in and you have checked some of the notes that I have attached for you to be deemed present. So you can attempt that question from now, and I'll expect to have your answers by 5 p.m. today.